All right, so let's talk about the early universe then. And here are the key ideas that you should take with you. That basically, because the way Big Bang is, universe was denser, smaller, that resulted in higher densities, and energy was also squeezed, so there were higher temperatures. And this is entirely predictable if you have the correct cosmological model. So at any given time, the temperature of whatever fills the universe, early on there'll be some kind of plasma, is related to the rest mass energy of those particles. So it's just like in the accelerator. If you want to generate particles of some mass, well, your accelerator should be able to accelerate whatever you're colliding, protons or other things, with comparable energy. So you create pairs of particles and antiparticles that will correspond to essentially thermal energy at the time. And then as you keep pushing closer to the Big Bang, energies are higher, interactions that matter change, there may be new kinds of particles, and so on. And it all kind of stops at the logarithmic scale around 10 to the minus 43 seconds after Big Bang. Why that? Well, maybe it doesn't, but that's so-called Planck time, which I will define later in the talk, and we don't think that we can really push further out. So this is the kind of plot that the physicists would put together, Mike Turner in this case. It kind of shows on a logarithmic axis the time, the characteristic energies, the temperature, and so on. And of course, all of the stuff that's actually observed is squeezed in the left corner, right, on the left side. And most of this logarithmic time axis that spans like 60 orders of magnitude is times when we don't really know what physics was like. So we have just speculative ideas about it. I'll talk about some of those. All right, so what evidence can we use to probe the early universe? The obvious first one is microwave background. So when the universe is a few 100,000 years old, and physics then is well understood atomic physics, plasmas and gases. We're very confident we can do that. But we can push closer in to sort of for milliseconds to about minutes, which is when we think that there was primordial nucleosynthesis, that temperature and density were such, like comparable to those in stellar cores, so that the universe was doing what stars do. It was fusing protons and neutrons into helium, and just a little bit of some heavier stuff. That too is a nuclear physics that we understand fairly well, and you'll see it makes really good predictions. Well, then there is another important observation, which is that there doesn't seem to be much antimatter anywhere we can see. I mean, except, tiny quantities that come from weird objects and so on. So why is that the case? Why isn't the universe symmetric in the amounts of matter and antimatter? But apparently it isn't. A lot of it annihilated in the early universe, but there is still excess of regular matter left. So understanding that is telling us something about physics. And then there is the inflationary scenario, which happens when the universe was maybe 10 to minus 33 seconds old. We absolutely have no physics for that, but we can kind of make hypotheses. And the only reason people take it seriously is it explains a number of important observations. And I mean, so well that it's really compelling. One of which is the universe is spatially flat, which seems to be the case. So the upshot of this is that cosmological observations can push to energies much higher than any accelerator we have on planet Earth for any predictable future. And so they probe fundamental physics in a way that's unique. So here are some of the kind of key moments, so to speak. I mentioned Planck era, age of 10 to the minus 43 seconds, when we're pretty sure quantum gravity must come into play, but we do not have theory of quantum gravity. Around 10 to minus 33 seconds is where a phase transition happens, which I'll explain later, and that's when inflation happens. It doesn't last very long. And around the same time, we think is where the strong and electroweak interactions split into two. Before that, there were like one interaction. I'll comment on that later. When the universe is a microsecond old is where we think that baryons form from quark soup into protons and neutrons. And then from about millisecond to about 3 minutes is where light elements form in the Big Bang. Then, as you already know, there is transition from radiation dominance to matter dominance, about 100,000 years. And then 380,000 years, that's where microwave background is released. The gas becomes neutral. And then after that, astronomy, observational astronomy begins. Stars and galaxies form and evolve. Yes?
How did they get so much theory on like just the first millisecond of universe?
Well, there is some amount of particle physics that can be used to suggest when quarks and antiquarks can recombine into making hadrons. In the same way that when nucleosynthesis happens and when atomic physics tells that hydrogen becomes neutral. We'll get to this in a bit. But you're right, the further, deeper in the past you push, more uncertainty it gets. I would say earlier than the cosmic nucleosynthesis, things are increasingly insecure. But there are reasonable hypotheses about it. So don't take this as a gospel truth. It is just what currently physicists think might have happened. And so this is one of those cartoons that kind of shows what happens when in a quasi-logarithmic fashion, and you can look at it at your leisure later. So, microwave background. As you remember, this is a trivial prediction. Once you understand the universe expands, you run the clock backwards. The universe is hot and dense at some point. And then as the universe expands, it gets cooler, less dense, plasma has to recombine, gas becomes neutral. And at that point, it becomes transparent to radio waves. And before then, it's a plasma which is conductive, and so it's opaque to radio waves and other electromagnetic radiation. So the original models from Gamov's group, Arthur and Herman, they estimated that there should be this diffuse radiation background that by now is redshifted to a black body of temperature of 5 Kelvin. And then people were trying to measure it through 1960s, saying that it was probably less than a few tens of Kelvin. And then finally, it was discovered or confirmed by Penzias and Wilson. But even before then, there was an evidence for the microwave background, and it was not recognized as such in 1941. And that is the observed lines of interstellar cyanogen. And the ratios of those lines are sensitive to the temperature, ambient temperature around those clouds. So they figure out, well, looks like there is radiation field of about 2 or 3 Kelvin, and that's why we see the ratios of lines. Nobody understood this until Fred Hoyle made a connection. So this is an interesting lesson that you can kind of see previously unknown phenomena, but not recognize them as such until the rest of the science is ready to figure out what's going on. So you probably do know a story about how Penzias and Wilson were working for Bell Labs trying to debug satellite communications and just couldn't get rid of this one source of noise, white noise, and that turned out to be microwave background. Bob Wilson, who's on the left here, was a Caltech student, so that sets the expectation level for you guys. And the measurements ever since got better and better and better. And this is actual measurement. The error bars were actually smaller than the thickness of this line. It's the most precise black body, more precise than any we can make in the lab. And then you subtract the black body from the data, and all the residuals are, well within the error bars. So there is no suggestion of deviations from the black body spectrum, because there were theories that suggested that, like if you had some kind of large energy release in the early universe, that will modify the spectrum. But no. All right, so typically ionized hydrogen nebulae are like 10,000 Kelvin. But if you look at this, it came from a time when the universe was like a little shy of 3,000 Kelvin temperature. Why is that? And the reason is that there are a billion times more photons than there are protons and electrons. And so just in the tail of the Boltzmann distribution, there is enough energy, 1 billionth of all photons, to ionize hydrogen, even when the bulk temperature is less than the normal ionization temperature, right? Here it tells you, it's 13.16 electron volts to do it. Plug in the black body spectrum, get 50,000 Kelvin. Well, it really recombined when the universe was between 2,500, 3,000 Kelvin. And that's why it has the redshift that it does. So divide that by a factor of 1,100, so you get 2.7 degree black body. It didn't happen instantaneously, of course. It took some time for that to happen. And so this curve shows you the computation of the fraction of neutral hydrogen as time went on. So beyond redshift of 1,600 or so, it was still fully ionized. By the time it dropped down to 1,200, redshift 1,200, 1,100, it was, I'm sorry, I swapped the labels. Those should be fully neutral and it should be fully ionized. I'll fix that. And so here is a little table to do that. So it's more like a fuzzy boundary. It's like a stellar photosphere that has an optical depth, right? That, there is not solid surface, but, it gets more and more opaque as you look deeper in. So that's basically the physics of microwave background, plus the whole story about acoustic oscillations that we went through the last time. But now let's push deeper in the universe. So when the temperature was high enough for thermonuclear reactions to occur, you had inverse beta decays, annihilations, and so on, and it will go in both directions. But remember that neutrons are slightly heavier than protons. So statistically, they'll be less favored. And so then that will lead to a discrepancy between them. And this is how it works. All right, so these are the basic inverse beta decay reactions, right? But in any thermodynamical system, in equilibrium, the particles will obey Boltzmann distribution, which hopefully you covered in physics classes. And when temperature was 10 to the 12 Kelvin, which is roughly what we're talking about, all right, then this was the ratio of the number of neutrons to number of protons, almost the same. But then, as the temperature keeps dropping due to the expansion of the universe, that ratio keeps changing. So eventually, when the universe is too cold to sustain these nuclear reactions, the ratio is 223 neutrons to every 1,000 protons. Okay. So the Big Bang nucleosynthesis is essentially driven, well, by the density parameter, but also the half-life of neutrons. You probably know neutrons are unstable, beta decay, about 15-minute half-life. And so that favors reactions in one direction, and about 25% of them are destroyed before they can combine with protons. All right, so when the temperature is billion degrees Kelvin, remember solar interior temperature is like 15 billion degree Kelvin. All right, they do the same thing more or less, form deuterium, helium-3, then helium-4, and then the universe expands, temperature drops, can no longer sustain thermonuclear reactions. So the universe will make helium, both helium-3 and helium-4, and stabilize it of hydrogen, deuterium. but it will also form trace amounts of a couple other light elements. And people who do these computations come up with diagrams like these and show what's the mass fraction of a particular type of nucleus as a function of time. And you can see there's a lot of action when temperature is, a billion degrees or so. But then it stabilizes in the asymptotic values, and they can compute expected abundances of helium-4, helium-3, deuterium. The number of neutrons keeps dropping because they decay, and even lithium and beryllium. Okay, so I'm missing an equation here. Okay, so when that happens, you get this neutron to proton ratio of 0.14 or so. And so therefore, protons will be about 75% of the total mass, 3/4 of the total mass, and 1/4 will be in the form of helium, right? But because the neutrons are now tied up in helium, which is stable, they don't decay in there, then that's not very sensitive to the matter density. But the other elements are. And so the universe expanded too quickly to form anything heavier than these very light elements. All right. Here we go. This is my missing slide. Right, so the same thing. All right, so when all is said and done, and I'll show you a plot of abundances in a moment, we can infer from cosmic nucleosynthesis and actual measurements of abundances of heavy elements, I'll show you a diagram in a moment, that baryonic density modulo Hubble constant squared will be in this range. Remember, little h should be about 0.7 because this is in units of 100 kilometers per second per megaparsec, so I'll multiply these numbers by 2. So it'll be roughly 4.5, 5% of the omega. And amazingly enough, this is an excellent agreement with the same number measured from microwave background fluctuations with completely different physics, completely different analysis, completely different measurements, which is reassuring. But okay, so here is how this cosmic barometry works, right? What's shown here are the green curve at the top is abundance of helium-4 by mass fraction. And it's much higher than the others because that's the dominant product. And you can see it's a fairly shallow curve. So it's not very sensitive to the baryon density, as I mentioned a moment ago. On the other hand, if you look at the deuterium curve, it drops rapidly the denser universe is. And that's because deuterium is so easy to burn, like in stellar cores. It has a very high cross-section. So if you have higher density plasma, thermonuclear plasma, you're going to get rid of more deuterium. And to a lesser degree, also helium-3. But deuterium is the steepest one and therefore provides, in principle, the best measurement of the baryonic mass density if you can measure the abundance of deuterium. Interestingly enough, it's almost impossible to make new deuterium except by spallation by cosmic rays. Cosmic rays hits a nucleus and one of the fragments is deuterium. But other than that, it's just burnt in stars. All right, how do we measure abundance of helium-4 in stars or stellar populations? Well, this shows helium mass fraction now in stars versus the oxygen abundance. Now, if all helium was made in stars, its abundance will be proportional to abundance of other things like helium or oxygen or carbon or nitrogen and so on. And this line would go through a coordinate origin. But if you start with a pre-existing amount of helium, then you just add a little bit, and you can squint and see that there is a little slope to this line. But the intercept at the zero metal abundance gives you primordial helium abundance, which is about 24% and change, which again is measured also from cosmic microwave background, and it's in an excellent agreement, and also with the models. All right, well, deuterium is then a great probe of the cosmic baryon density, so how do we go about it? And the way this is done is using spectra of quasars. As you may know, that there are so-called intergalactic Lyman alpha clouds, little clouds of hydrogen left over from galaxy formation. They're mostly ionized, but not entirely. And if you look at the bright source of ultraviolet light in the background, such as a quasar, then whenever the line of sight intersects one of those clouds, you're going to have a little absorption line. Now, if the cloud you're intersecting is reasonably optically thick, you're going to have saturated absorption. Those are so-called damped Lyman alpha systems. And deuterium is mixed with hydrogen. However, because deuterium has a higher mass, its atomic line transitions are shifted from those of simple unprotoned hydrogen. And the amount of shift corresponds to a velocity shift of like 86 kilometers per second. So you want to find intergalactic clouds that have sufficient column density of hydrogen for deuterium line to be detectable, but not too high a density so that it's totally lost in the damping wings of the regular hydrogen line. And people like David Teitler at UC San Diego have been doing this for a long time, and they derived this measurement of the current primordial deuterium abundance at high redshifts, and that's again exactly in agreement with what we get from microwave background and other isotopes. So you can push this to other things. You can use primordial nucleosynthesis to constrain the number of neutrino species in the early universe, or lepton families, if you will. And the answer is 3. That's what's allowed. Again, you can confirm that with microwave background measurements, which are completely different physics. They're really, microwave background is telling you what's going on when the universe is 380,000 years old. Primordial nucleosynthesis is telling you what's happening with like second volt, right? All right, so this is pretty much where well understood physics of the early universe ends. Now, let's go to a really, really early universe and the idea of inflation, which came out by Alan Guth, who was a cosmologist at MIT. It was already kind of discussed by a couple other people, Demosthenes Kazanas and Alexei Starobinsky in Soviet Union, but it didn't really catch on. But Guth understood what he was doing and he made a big noise about it. And this is actually a copy from his notebook, which says, spectacular realization, and then says why this is. And I'll show you in a moment why that is. And that became very fashionable. A number of other people, including Andre Linde, shown here, worked on it, came up with more complex stories about inflation, the so-called chaotic inflation, and so on. Well, why did everybody got so excited? Because the inflation explained 3 big problems for which there was no explanation up until then. Why is the universe so close to being flat? Why is cosmic microwave background so uniform? And also, why are we not detecting magnetic monopoles, which you can say, well, okay, fine, that's some kind of theoretical fiction, but if you believe certain types of theoretical physics, you expect to be a lot of magnetic monopoles around, and there aren't any. It's also explaining for the density power spectrum of large-scale structure, which we'll study later, and it makes one new prediction. That is, what will be the spectrum of gravitational wave background from density fluctuations in the early universe. And that is a very hard thing to measure, but people who using pulsar timing to detect really long wavelength gravitational waves passing through the solar system think that that might be kind of on the verge of detecting that in the next few years, perhaps no more than 10 years, which would be spectacular. Okay, so what are these flatness problem and horizon problem? Flatness problem is this. If you look at the expanding universe, if you ask what's the value of omega as a function of time? You start with something, and then it will either go up or down. And it goes in the direction of deviating from flatness. So today, as you saw earlier, it's like limiting omega of curvature to parts in 1,000 or something. So it's pretty close. In order to achieve that today, it had to start much, much, much closer to unity to not deviate from it as much. Here is a plot from Ned Wright, which I think is a spectacular illustration of this. And he computed what would scale factors look like. The black line is scaled version of density today, right? When the universe was a nanosecond old. And you can see how many digits there are. You change this by plus or minus 1 gram per cubic centimeter at 1 nanosecond age, and you get either green or the red curve. So this had to be tuned to a phenomenal precision to be so close to the flatness today. What's the horizon problem? Well, all right, we can consider just the Einstein de Sitter universe because that's a good description early on. And there is a scale factor dependent on time. So horizon distance, how far is the most distant thing that you could have received signals at that time is given by the expansions of factors as a function of time. And beyond that, you couldn't, in principle, receive any information. Later, that the horizon expands as time goes on, you could. But back then, that was it. And so when the pattern of density fluctuation is frozen at the epoch of decoupling, in principle, regions that are larger than the horizon size then were not in a causal contact. Okay? And that turns out to be about a little less than 2 degrees on the sky. And yet, here is the map of the cosmic microwave background. And you recall that these bumps are about 1 degree in size. So each of these little blobs, or regions that are like less than 2 degrees on the side, in principle, was not in a causal contact with any others. And yet, over the entire sky, they're the same temperature to parts in a million. How did they know to be so well thermalized? Well, the answer inflation gives you is that they used to be in a causal contact, but then they were carried apart. All right, so how does that work?
Question.
Yes?
Why couldn't they all just have happened to be the same temperature? Like, why does that tell us that they probably are causally connected somehow to different blobs?
Density fluctuations are random. They ostensibly come from quantum fluctuations in an even earlier universe. And so they would have to be spectacularly well tuned to be just that amplitude and nothing else, right? I mean, there is no reason why some regions of the universe wouldn't be much denser or much less dense and expand on an entirely different scale, right? So here you have things that are hundreds of times or even thousands of times the horizon distance, and yet they know to have the same temperature. There was no communication between them in principle. Okay, so here is the story. It posits that at some early times, there was some quantum field that provided a sort of energy density of physical vacuum, just like cosmological constant dark energy is today. But this is a different one. This one is long gone. Now, in quantum mechanics, when you look at any quantum system, you can either know that some energy level is the ground level, or you can know what its level is, but you can't know both at once. And if there is some grand unified field that fills up the universe, then it could have different energy levels, right? So there is a more complex story that includes Higgs boson and so on. But the basic idea is that, well, physical vacuum is not empty, just as we know now. I mean, that there could be energy density of a physical vacuum. And back then, apparently, there was. But it was unstable. And so just like unstable energy level in an atom will decay and send out a photon and go to the true ground level, the idea is that from this false vacuum, false because it's not the ground state, the universe decays to the lower state, the actual ground state, and in that process, you generate a great deal of energy, just like atom emits photons. The other way of thinking of this is like phase transition, and that's indeed the mathematical apparatus that's used, just like that, you know, if you are heating up ice, at some point it's going to melt. If you heat water, at some point it's going to boil out. And so similar thing happens in the very early universe, and that was the idea behind the inflation. Now, why does that help? Hold on. So once you look at this as a phase transition, you can think of that very early physical vacuum in early universe boiling over, just like a water boils over, creating bubbles, each of which becomes an expanding universe. And early on, they're close together, so they really can collide, and that's what generates a lot of energy density in those. So people actually look for signatures of our universe colliding with another universe bubble in microwave background, and there isn't any, right? So this may or may not actually be true, considering that we don't really have the physics of this, although thousands and thousands and thousands of papers have been written about it, like why inflation starts, why it ends. But because of the consequences that you'll see in a moment, people think this is worth thinking about. Yes?
Is this kind of similar to, I heard something about like the vacuum collapse, so I can't remember if that was the same thing as string quarks, but like the fact that we're in some kind of false vacuum, deviation, the whole.
Yeah, in principle, it could happen, but it would go in the other direction. That would generate a new cosmological constant that will expand current universe dramatically. But again, since we have no physics of this is a pure speculation. Who knows, right? So yeah, we can end the universe with careless handling of high energy particles. All right, so the simple description of this in Friedmann-Lemaitre models is essentially pure cosmological constant, energy density of a physical vacuum. And that, as you recall, when you neglect everything else, gives you a very simple differential equation, and the solution is an exponential expansion. So, for some reason, instability in the primordial hypothetic quantum field, inflation is initiated, and then the universe expands by about 100 e-folding times, or 43 orders of magnitude. And then for some reason it ends, and people still figuring out what are the viable mechanism for inflation to end. So the density parameter has been evolving over, well, 43 orders of magnitude, and it's still pretty darn close to 1, which meant it had to, at the end of inflation, it had to be incredibly close to unity. So if you were to plot schematically what that looks like, you have false vacuum, universe expands, suddenly this energy transition happens, and it goes down to true level of vacuum. Size drops by 40-some orders, increases by 40-some orders of magnitude, and then continues proper Friedmann-Lemaitre model. Well, why does that help? It helps solve the flatness problem because whatever the curvature radius of the original region in which everything we see in the sky now was, it expanded by 40 some orders of magnitude. And so curvature today will be totally negligible. This is why flat Earth conspiracies live. Look at it, it looks flat to me. And that's because the region you can see is much smaller than the size of planet Earth, right? And so the same thing happens here. We are in some curved spacetime, but the curvature radius is so huge that it's essentially flat to an incredible precision in the universe in which we live. So it's omega is equal to 1 plus or minus epsilon, and epsilon is like a really small number.
Is this saying that the closed and flat universe models are equivalent?
No, it could be also negatively curved in principle, but this is just an illustration. Same thing would apply to look at the saddle surface that has negative curvature. Right? It could be plus or minus epsilon. Yes?
So wait, how exactly does this get rid of the fine-tuning problem? Is it we're essentially in something that's almost 1 plus or minus epsilon, and then it expands out? And then
No, it ends at omega of plus or minus epsilon because it expanded dramatically to a curvature radius that's huge.
But I thought we had talked about earlier with solving the Friedmann equation that like it goes away from 1. It diverges away from 1 if you change it even by a little bit.
Right. Yes, but the density matter is carried by the expanding spacetime, right? And it's essentially tightly coupled on the curvature radius in this case, which, I mean, I think this is as good intuitive explanation as any. But yeah, I mean, whatever it started with, it could have been highly curved over dense region, but it gets expanded dramatically by vacuum energy, which doesn't act like the regular matter energy. And now it's something that's essentially flat Euclidean space. How about the horizon problem? How comes that there are different parts of the universe you see now back at the epoch of recombination that were not in causal contact, and yet they knew to have same temperature? It's because they were all together at one point. They were just carried apart by the inflation. So they really were in mutual causal contact before the inflation. Inflation takes them apart, because remember, space can expand faster than the speed of light. And then gradually in time they catch on as their horizon grows during the normal Friedmann limiter expansion. So it's a very elegant solution for these two problems, which otherwise had no explanation whatsoever. I mentioned that also inflation leads us into understanding something about structure formation. So the idea is that in a really, really early universe, pre-inflation, there are quantum fluctuations, particle, antiparticles, whichever particles were then, form and annihilate. And so that creates a kind of Gaussian noise on microscopic scale. But then these microscopic scale fluctuations get inflated by 40 some orders of magnitude. And so today they would correspond to the large-scale structure stuff that we see, or to those baryon acoustic oscillations. So if you start with quantum fluctuations and just inflate them dramatically, you'll create density field with a certain density power spectrum, and it's exactly what we see at large scales. So this was not prediction of the inflation because we already knew what that spectrum was, but it was good consistency check. All right. So inflation is compelling, but not proven. It's based on physics that we don't have yet, and we can just speculate about. But there are different inflationary models, and they have some parameters, and microwave background measurements can narrow down the range of possible models, but they cannot tell us whether it actually really happens, because the only prediction that we can possibly test is existence of cosmic gravitational wave background with a particular power spectrum. But it is compelling because we have no other way of understanding the flatness problem and the horizon problem, and never mind the magnetic monopoles. Okay, so let's push to even earlier universe. Now, in particle physics, we know there are 4 basic interactions: gravity, strong, weak, and electromagnetic. And it was established some time ago and demonstrated through experiments and accelerators that electromagnetism and weak force, responsible for beta decay, are just 2 facets of the same interaction, which split when universe was, I forget, here it says 0.1 microsecond old. So as the ambient energy, if you will, increases as you push closer and closer to Big Bang, slightly different physics happens. And so there is a phase transition that splits these 2 interactions, and they're actually experimentally verified. Well, then people said, well, what about strong interaction? Well, the same kind of reasoning applied then, and was hypothesized that indeed, when the universe was about 10 to the minus 35 seconds old, there was another phase transition that split strong and electroweak interaction, and maybe that was what was driving the inflation, although we don't really know for sure. At some point, well, they were same as gravity, so when does that happen? Well, our best guess is it happens when the universe is 10 to the minus 43 years old, and so that's sort of the ultimate theory of everything in grand unification, when gravity is unified with the other fundamental interactions. Trouble is, we do not have the physics to push to that level, and Lord knows we have no way of experimentally testing it yet. Okay, so just a few words about the other 2 phase transitions. The electroweak era is up until the universe was 10 minus 10 seconds old. Okay, and well, you can read this for yourselves. And then grand unified theories, which was a grandiose name that Mike Turner gave them, is those that unified strong interaction with electroweak interaction, and that happens at much earlier stage. So it's speculative but plausible idea, and the details we do not know. Well, one of the observables that I mentioned in the beginning is that we know that the universe has a lot more matter than antimatter. And originally, due to symmetry and parity, it should have been the same. But we now see that there is, well, something like a billion photons for every proton. And so there had to be that discrepancy in the number of matter particles, antiparticles, at whatever era this happened, way before protons existed, all right? So there is one theoretical picture how this may have happened, and it's due to the Andrei Sakharov, 1960s. And so he came up with 3 conditions that had to be satisfied in order to violate symmetry between matter and antimatter. As you probably know, particle physics thrives on symmetries and symmetry violations, okay? So you ought to be able to violate the baryon number conservation. And that was never seen, but it's predicted might have happened in these grand unified theories. You also need charge and charge parity violation, and that was actually confirmed experimentally back in 1960s. And you need departure from equilibrium, and that's provided by expanding universe. So if there is a physical mechanism that will violate baryon conservation, you could start generating a symmetry between matter and antimatter. This is beyond our ability to test, but it's a plausible explanation for what's simply an observed fact, that we live in totally matter-dominated universe. Okay, well, back to what we call the Planck era. Back in 1899, Max Planck asked, why do we use units that are based on something like a fraction of meridian that goes through Paris or length of some rod and so on? Are there natural units in that physics gives us? And so he started playing with three fundamental constants known at the time: Newton's gravitational constant, his own Planck's constant, and speed of light. And when you do combinations like that, you can come up with natural measurements of time and space and mass and charge and temperature or energy and so on. And if you look at the last column, well, there it is, the Planck time, roughly 10 to the minus 43 seconds or so. Planck length, 10 to the minus 33 centimeters. Planck mass, 21 micrograms, and so on. And we have no reason to believe that these define a special epoch in history of the universe, but they might, because physical constants achieve certain value due to physics that we do not yet have, and then the natural time this could have happened is around Planck time. Okay? Now you can use these combinations to generate units for anything else, just like people do from SI system and CGS. So it's not obvious why Planck units should define this earliest era where ostensibly quantum gravity comes into play and splits from other interactions, but it's kind of the best guess we have. Well, what about physics before Big Bang? Brave people even try to do that, right? And Big Bang as an infinite density comes really from just extrapolation of a classical theory of relativity. And physics doesn't do that. But unfortunately, we do not have physics of quantum gravity that will help tell us what happened before the Big Bang, if there was before. And it's not for the lack of trying.